So now let's turn our attention to another periodic property known as ionization energy. Now, it's fairly simple to understand what ionization energy is, if I could spell properly, which I can't, so I've got to stop and start again. So let's examine another periodic property known as ionization energy. And it's fairly simple. Ionization energy is literally the energy needed if you had a neutral atom such as sodium. Its electrons aren't just going to wander away. If you're going to remove an electron from sodium or ionize it, it's going to require you to do work. You're going to need energy. And that's exactly what ionization energy is measuring. Literally, how much energy, how much work must be done on a neutral atom in order to ionize it, remove one of its electrons. Now, there are two general trends that we see. One is within a given group on the periodic table, such as group 8 or any other group. Generally, we're going to see an increase in ionization energy as you move up through the group for a very simple reason. The only thing that's changing from atom to atom within the same group is the valence level. That is the reactive level of electrons. And of course, the closer the valence electrons are to the nucleus, the more control the nucleus has over those electrons, the greater the attraction. So you're going to have to add more energy to remove an electron if it's in a lower valence level. And that's why we see this general increase as you go up through a group, because the electron from, say, radon would be coming from the 7th principal energy level, whereas that from helium is coming from the lowest possible energy level of n equals 1, very close to the nucleus. So it gets progressively harder to ionize the atom, and therefore it requires progressively more energy. However, as we move across a period, we know that there is no change in valence level. However, what we do know is there's an increasingly larger effective charge as you go from group 1 to 2 and on to the noble gases in 8. And of course, that means generally you'd expect to see a higher and higher ionization energy increasing left to right across the periodic table. And for very good reason. An atom that has a greater effect, say oxygen of +6 on its valence electrons, compared to, say, beryllium, which only has a +2 effect, it's going to be much harder to remove an electron from an atom that's got a greater effect on its valence electrons. And therefore, it's going to require you to do more work, and hence you'll need more ionization energy, greater ionization energy. So yes, generally that's true. As you go left to right, the ionization energy increases. That said, there are two glaring exceptions to the general increase left to right of ionization energy. And one of those exceptions occurs when you transition from group 2 to group 3 in the periodic table. Yes, a boron atom has a greater effective charge than a beryllium atom. It's 50% greater. It's +3 versus +2. But in fact, the ionization energy decreases as you go from group 2 to group 3. Why? Well, very simply, if you looked at the valence configurations for beryllium and for boron, for beryllium, you'd see a 2s2 configuration. But for boron, the group 3 atom with 3 valence electrons, it's 2s2, 2p1. Now, very simply put, it is going to be easier to remove a p sublevel electron from the group 3 atom than one of these s sublevel electrons from the group 2 atom. And that's because a p sublevel electron already has more energy than an s sublevel electron, and it's significantly greater energy, as a matter of fact. And because the p sublevel electron has so much more energy than the s sublevel electron, it's in fact easier to ionize rather than harder, despite the greater effective charge of the group 3 atom. And the other major exception to the generally increasing trend left to right in ionization energy occurs between a group 5 and group 6 atom, which are also side by side. Now, we cannot explain this in terms of different sublevels of energy for the electrons being removed, because after all, we're going to be removing an p electron from nitrogen just as we'll be removing a p electron from oxygen. So why would it in fact be easier to remove one of the oxygen p's with a greater effective charge than one of the nitrogen p's? Well, the answer is in looking at the orbital diagram of the p sublevels. For instance, if we look at nitrogen, we know it has 3 p sublevel electrons. And in the orbital diagram, according to Hund's rule, those 3 electrons would be in separate orbitals. Unpaired is the key phrase. Now, if you look at oxygen, which also has 2p as its valence level, sublevel being filled, it has 4 electrons to distribute in these 3 orbitals. So, of course, 3 of them would go into individual orbitals, but then the 4th electron would be paired up with another electron. And this is the key to understanding why, in fact, it's easier to ionize oxygen than nitrogen, because the electron being removed from oxygen is paired with another p electron in the same orbital. But none of the electrons, it doesn't matter which one you remove, coming from nitrogen, is paired. Consequently, this paired electron experiences repulsion from the other electron in the orbital, and that repulsion provides a bit of a boost, tries to shove its orbital mate out of the way anyhow. So if it's already experiencing this push, this repulsion from its own valence orbital partner, it's going to take less energy to remove it altogether from the atom, as opposed to the nitrogen's electron, which is unpaired and not experiencing the same electron repulsion. So yes, despite the fact that oxygen has a greater effective charge than that of nitrogen, it is easier and requires less energy to remove a paired p electron from oxygen versus an unpaired p electron from nitrogen. And we see that discontinuity, this decrease instead of increase between 2 and 3 and 5 and 6 in both the first and second periods of the periodic table. So as some further illustrative examples, if I were to just randomly pick a couple of a couple of atoms, such as chlorine and bromine, and I asked who has the higher ionization energy and why, well, I'd have a higher ionization energy for an atom whose electron was being ionized from a lower valence level. And since chlorine has a valence level of n equals 3, and that for bromine is n equals 4, it will be harder to ionize an electron from the lower valence level of chlorine as compared to that of bromine, and therefore chlorine would have a greater ionization energy. Now, if instead I were to pick, say, silicon, pen color, silicon, and aluminum as comparison. Now, I remind myself that as I go left to right, an effective charge is generally the argument. And I just check to make sure it's not between groups 2 and 3 and 5 and 6. And 3 and 4 is not an exception. Very simply put, because the effective charge of silicon is +4, and that for aluminum is only +3. It will require more work to be done to remove an electron from an atom with a greater effective charge than from one with a lesser effective charge. So in fact, silicon has a higher ionization energy than that of aluminum. Now, don't give antithetical explanations when you talk about ionization energies. In other words, if I want to compare carbon and silicon and I want to know who has the lower ionization energy, well, I know it's going to be a valence level argument, but it will take less energy to remove an electron from a higher valence level. So if carbon has n equals 2 as its valence level, and silicon's is n equals 3, Silicon will have a lower ionization energy because the electron being removed is coming from a higher valence level. Now, if we compare atoms side by side for effective charge arguments, and no, groups 6 and 7 are not an exception, I would want to couch the argument for lower ionization energy in terms of who has the weaker effective charge. Less of an effect by the nucleus would make it easier to ionize the atom. Therefore, if sulfur has a +6 effective charge and that of chlorine is greater, +7, I would say by virtue of a lesser effective charge, it will require less energy to ionize sulfur than chlorine. And I would treat the exceptions the exact same way. Be careful whether you're answering higher or lower ionization energy and why. Now, if I'm comparing magnesium and aluminum, even though the general trend is an increase left to right, I know this is an exception. And if I wanted to know who has the higher ionization energy and why, I'd actually go with the magnesium. But the reason is, of course, a sub-level argument. The electron coming from magnesium is one of those s sublevel electrons, but the one that would be ionized from aluminum is coming from a p sublevel. Because s sublevel electrons have so much less energy than p sublevel electrons, it will in fact require more energy to remove an electron from magnesium. It has a higher ionization energy. Now, if I've been asked which of these two has a lesser ionization energy, I go with the opposite argument. Because a p sublevel electron already has far more energy than an s sublevel electron, it will be easier and require less energy to ionize the aluminum than the s sublevel electron from magnesium. And when you get to a group 5 and group 6 atoms side by side, again, that violates the general increasing trend that we see left to right of ionization energy. So I know that phosphorus would have the greater of the two, but the reason there again is because the electron coming from phosphorus is one of those unpaired p electrons with nothing to repel it, give it that boost out of the sublevel, whereas the electron in the sulfur atom, the group 6 atom, is going to be paired with another electron, and that makes it easier to ionize. So if I were saying who has a lower ionization energy and why, I'd say the group 6 atom sulfur, because the electron being ionized is a paired electron experiencing greater repulsion than the unpaired electron from phosphorus. And if I said who has the higher ionization energy and why, I would go with the phosphorus, because the electron being ionized is unpaired. It isn't being given that little boost outward from the orbital, and therefore it's going to be harder to ionize than the sulfur electron, which is, of course, paired up and being repelled by the other electron in its orbital.